Welcome! In this session, we'll explore an intriguing problem titled Make two arrays equal by reversing subarrays. We'll break down the problem, analyze different approaches, and derive an efficient solution. Let's dive in. In this problem, you're given two integer arrays, target and ARR, both of the same length, n. The goal is to determine whether you can make the array ARR equal to target by performing a specific operation any number of times. The operation allows you to select any non-empty subarray of ARR and reverse its order. The task is to return true if it's possible to transform ARR into target using this operation, or false if it's not. Both arrays are provided as inputs, and the output is a Boolean value that indicates whether the transformation is achievable. To better understand the problem, let's go through some examples. In the first example, target is 1 2 3 4 and ARR is 2 4 1 3. Here, you can reverse the subarray 2 4 in ARR to get 4 2 1 3. Then, by reversing the entire array, you can achieve 1 2 3 4, which matches target. This means the output is true. In the second example, both target and ARR are 7. Since they are already equal, no operations are needed, so the output is also true. Now, consider two more examples. In the third example, target is 1 12 and ARR is 12 1. Reversing the entire array ARR gives 1 12, which matches target, so the output is true. However, in the fourth example, target is 3 7 9 and ARR is 3 7 11. Here, the elements of the two arrays don't match. 11 is in ARR but not in target, and 9 is in target but not in ARR. Since the elements are mismatched, it's impossible to transform ARR into target, so the output is false. This problem also comes with some constraints and observations. The length of both arrays, n, is guaranteed to be equal, and it can go up to 100,000. Each element in the arrays is between 1 and 1,000. Since reversing any subarray allows you to freely change the relative positions of elements, the problem simplifies to checking if both arrays have the exact same elements with the same frequencies. Efficient approaches to solve this include sorting both arrays or using a frequency map. Let's also consider edge cases. If the arrays are already equal, like target equals 5 and ARR equals 5, the output is true. If the arrays contain duplicates, such as target equals 1 1 2 2 and ARR equals 2 2 1 1, the output is still true because the elements and frequencies match. However, if the frequencies differ, like target equals 1 1 2 and ARR equals 1 2 2, the output is false because the counts of 1 in the arrays are not the same. To begin, let's consider a brute force approach to solving this problem. The idea here is to simulate all possible subarray reversals in the array ARR and check if any sequence of these reversals can transform ARR into the target array. While this may theoretically work, implementing it would involve generating all possible combinations of subarray reversals, applying them one by one, and then verifying if the resulting array matches target. The main drawback is the sheer number of possibilities. Because there are an exponential number of ways to reverse subarrays, the time complexity grows factorially, specifically n, in the worst case, where n represents the length of the array. This makes the brute force approach computationally infeasible, even for relatively small input sizes. As a result, while it's conceptually correct, this approach is discarded due to its impracticality for real-world use. Now, let's focus on an optimized approach that leverages a key observation about the problem. When you reverse a subarray, the frequency of the elements in the array remains unchanged. This means that for ARR to be transformable into target, both arrays must have exactly the same elements with identical frequencies. Based on this, we can bypass the need to simulate reversals altogether and instead compare the frequency counts of elements in both arrays. The process is straightforward. First, calculate the frequency of each element in target using a hash map or Python's collections accounter. Then, do the same for ARR. Finally, compare the two frequency maps. If they match, we know ARR can be transformed into target. If not, it cannot. This approach is highly efficient, with a time complexity of n, as we only need to iterate through each array once to compute the frequencies, and a space complexity of u, where u is the number of unique elements in the arrays. By focusing on the invariant property of frequency counts, this method avoids the computational overhead of simulating subarray reversals, making it a scalable and practical solution. The chosen strategy builds on the insight that subarray reversals have no effect on the frequency of elements in an array. Recognizing this simplifies the problem significantly, reducing it to comparing the frequency distributions of ARR and target. To implement this, we can use Python's collections counter to compute the frequency of elements in both arrays. Once we have the frequency counters, a simple comparison determines whether the transformation is possible. This strategy strikes an excellent balance between correctness and efficiency. Compared to the brute force approach, which is computationally prohibitive due to its factorial time complexity, the optimized approach is elegant and practical, with a linear time complexity and minimal space requirements. By leveraging the mathematical property of frequency invariance under subarray reversals, this method avoids unnecessary computation while directly solving the problem's core challenge. Its clarity, efficiency, and scalability make it the definitive choice for tackling this problem effectively. The problem involves determining whether we can make two arrays, RR and target, identical by reversing any subarray of ARR as many times as needed. To solve this, we begin by checking if the lengths of the two arrays are the same. If the lengths differ, it's immediately impossible to make the arrays equal, as reversing subarrays cannot create or eliminate elements. Next, we sort both arrays. By comparing their sorted versions, we ensure that the frequency of each element in ARR matches the frequency in target. If the sorted arrays are not identical, we can conclude that no amount of reversals will make the arrays equal, and we return false. This initial sorting step is crucial because it confirms whether the two arrays are permutations of one another, which is a necessary condition for the transformation to be possible. If the sorted arrays are the same, we then check whether the relative order of elements in ARR can be rearranged to match target. This is where we use the union-find data structure, also known as disjoint set union, to determine which indices can be grouped together based on reversibility. The goal here is to group indices from ARR and target that can be swapped via subarray reversals. To do this, we iterate through both arrays simultaneously. Whenever an element in ARR matches the corresponding element in target, we union their respective indices. This union operation effectively connects indices that can be freely swapped, creating connected components. Finally, we verify if all indices with the same value belong to the same connected component. If they do, it means the elements of ARR can be rearranged to match target, and we return true. Otherwise, we return false. Sorting and comparing the arrays ensures that both arrays contain the same elements with identical frequencies. This guarantees that the transformation is possible in theory. However, the union-find step is critical for checking reversibility. It tracks which indices are connected and can be swapped via subarray reversals, allowing us to determine if the relative order of elements can be adjusted. This data structure is especially efficient because it supports two main operations: find, which determines the root of a set, and union, which merges two sets. By using path compression and union by rank, these operations are optimized to run in nearly constant time. Edge cases are also handled seamlessly. If ARR and target are already equal, the algorithm quickly confirms this. If duplicates exist in the arrays, the union-find structure correctly manages them by ensuring that all indices with the same value are grouped together, preserving the reversibility condition. Now, let's examine the complexity of this approach. Sorting both arrays takes log n time due to the sorting step. The union-find operations, including unions and finds, are nearly constant time per operation, so processing all indices results in n time. Therefore, the overall complexity of the algorithm is dominated by the sorting step, which is log n. Let's break this down with an example. Suppose we have ARR as 1, 2, 3, 4, and target as 2, 1, 4, 3. First, we check the lengths. Both arrays have a length of 4, so we proceed. Next, we compare their sorted versions. Sorting gives 1, 2, 3, 4 for both arrays, so they are identical, and we move forward. Then, we perform union operations based on matching values. For instance, our 0 equals 1 matches target 1, so we union indices 0 and 1. Similarly, we union indices for all other matching values, forming connected components. This ensures that the indices can be swapped appropriately using subarray reversals. After completing the union operations, we verify the connected components. In our example, all indices are connected as required, so we conclude that ARR can be transformed into target, and we return true. To optimize this algorithm further, we can use efficient sorting algorithms for larger datasets to minimize the time spent in the sorting step. Additionally, the union find structure can be further optimized by implementing path compression and union by rank, ensuring that each union or find operation remains efficient. Another optimization is to terminate early if the sorted arrays differ, avoiding unnecessary computations. With these optimizations in place, the algorithm efficiently handles a wide range of inputs, ensuring correctness while minimizing computational overhead. The problem requires checking if we can make two integer arrays, RR and target, equal by reversing any subarray of RR as many times as needed. The key observation here is that reversing subarrays does not alter the frequency of elements in the array, it only changes their order. Therefore, if ARR can be rearranged to match target, their sorted versions will be identical. The implementation is straightforward. 1. We define a function can be equal inside the solution class. 2. This function takes two lists as inputs, target and ARR. 3. Inside the function, we sort both target and ARR using Python's built-in sorted function. Sorting reorders the elements of both lists in ascending order. 4. We then compare the sorted versions of the arrays. If they are equal, it means ARR can be rearranged by reversing subarrays to match target, so we return true. Otherwise, we return false. This approach is efficient with a time complexity of O(n) log n due to the sorting operation. The solution also handles all edge cases, including empty arrays, arrays with duplicate values, and arrays with a single element, because sorting and comparison work universally for these scenarios. This concise and efficient implementation ensures correctness while maintaining clarity. This is the Java implementation of LeetCode problem number 1460, make two arrays equal by reversing subarrays. The logic mirrors the Python solution, both arrays are sorted, and then compared for equality using Java's arrays.sort and arrays.equals methods. Key differences include explicit type declarations and the use of Java's built-in utility classes to handle array sorting and comparison. This ensures the solution is efficient and concise while adhering to Java conventions. In this example, we are tasked with determining if we can make the ARR array equal to the target array by reversing subarrays. The target array is 1, 2, 3, 4, and the ARR array is 2, 4, 1, 3. First, the can be equal method is called with these two inputs. Inside the function, the approach begins by sorting both arrays. Sorting the target array gives 1, 2, 3, 4, while sorting the ARR array also results in 1, 2, 3, 4. Next, the function compares these two sorted arrays. Since they are identical, the function concludes that ARR can be rearranged to match target by reversing certain subarrays. Therefore, the function returns true as the final output. Here, we look at a case where the arrays contain different elements, making it impossible to make them equal. The target array is 1, 2, 3, and the ARR array is 1, 1, 2. The can be equal method is called with these inputs, and the process starts by sorting both arrays. Sorting target results in 1, 2, 3, while sorting ARR gives 1, 1, 2. When these sorted arrays are compared, they are found to be different. This discrepancy means that it is not possible to rearrange ARR to match target, even with unlimited reversals of subarrays. As a result, the function returns false, indicating that the transformation is not possible. Now, we consider a scenario where both arrays contain repeated identical elements. The target array is 7, 7, 7, 7, and the ARR array is 7, 7, 7, 7. The can be equal method is invoked, and the process begins by sorting both arrays. Sorting target results in 7, 7, 7, 7, and sorting ARR also produces 7, 7, 7, 7. When these sorted arrays are compared, they are found to be identical. This indicates that ARR can already be considered equal to target, as no reversals are even necessary. Consequently, the function returns true, confirming that the transformation is valid. This brings us to the key insight behind the solution. The problem allows reversing subarrays in ARR to make it equal to target. By sorting both arrays, we essentially standardize their arrangement into a canonical order, which eliminates the need to explicitly reverse subarrays. If the sorted versions of target and ARR match, it confirms that ARR can be transformed into target through some series of reversals. However, if the sorted arrays do not match, then no sequence of reversals can make the arrays equal. This insight simplifies the problem to just sorting and comparing the two arrays, making the solution both efficient and elegant. The time complexity of the solution primarily hinges on two operations: sorting the arrays and comparing them. First, sorting an array of length n is done using an efficient algorithm like timsort, which has a time complexity of O(n*log n). Since both the target and ARR arrays are sorted independently, the total time complexity for this step is twice that of a single sort, but constants are ignored in big O notation, leaving us with O(n*log en). Next, the equality check uses the equal sign operator, which compares the sorted arrays element by element. In the worst case, this comparison involves traversing all n elements, taking O(n) time. However, when combining these steps, the sorting operation dominates because O(n*log n grows faster than O(n) as n increases. Therefore, the overall time complexity of the solution is O(n*log n). Now, let's analyze the space complexity of the solution. The primary contributor to space usage is the sorted function, which creates a new array to store the sorted version of its input. Since we are sorting both the target and ARR arrays, this requires O(n) additional space for each array. Combining the two, the total auxiliary space is O(n) plus O(n), which simplifies to O(n). The memory used by the input arrays themselves does not count toward additional space usage since they are provided as part of the problem's input. Finally, the equality check using the equal sign operator does not require extra memory, as it directly compares the two sorted arrays. As a result, the overall space complexity of the solution is determined entirely by the auxiliary space used during sorting, which is O(n). When comparing this sorting-based approach to a brute force method, the efficiency becomes clear. A naive approach would involve generating all possible permutations of the ARR array and checking if any of them matches target. However, generating permutations has a time complexity of O(n), which grows exponentially and becomes infeasible for even moderately sized arrays. On the other hand, sorting provides a much more efficient solution with a time complexity of O(n*log n). The reason sorting works is that reversing any subarray does not affect the frequency of elements in the array. By sorting both target and ARR, we can efficiently verify if they contain the same elements in the same counts. This approach is consistent in its performance, as the time complexity remains O(n*log n, regardless of the input configuration. Similarly, the space complexity is also stable at O(n), as the auxiliary space required by sorting remains proportional to the input size. Finally, the correctness of this solution can be justified with a mathematical proof. Sorting the target and ARR arrays ensures that their elements are placed in the same order. If the sorted versions of these arrays are equal, it confirms that both arrays contain the same elements in identical frequencies. Given that the problem allows unlimited subarray reversals, this equivalence guarantees that ARR can be rearranged to match target. This is because subarray reversals only change the order of elements, not their counts. Therefore, sorting is sufficient to solve the problem, and the time and space complexity of O(n*log n and O(n), respectively, are both optimal for this approach. One of the most common mistakes in this problem is assuming that a single subarray reversal will always be enough to transform ARR into target. This is a misconception because the order of elements in the arrays might require multiple reversals, especially if the structure of ARR is fundamentally different from target. Instead, you need to consider all possible reversals or rely on specific properties of the problem to simplify your approach. Another issue is using inefficient brute force algorithms. These methods, which attempt all possible combinations of subarray reversals, can quickly become computationally expensive, reaching time complexities of O(n)³ or worse. For larger arrays, this is simply not feasible. The correct way to handle this is by optimizing your approach, perhaps using greedy techniques or leveraging efficient data structures. Lastly, not accounting for edge cases can lead to errors. For instance, scenarios like empty arrays, completely reversed arrays, or arrays with duplicate elements often expose gaps in logic. Always analyze these edge cases carefully to ensure your solution holds up under unusual inputs. Another common pitfall is ignoring the constraints and guarantees provided in the problem statement. For example, if the problem specifies that ARR and target contain the same elements, failing to validate this could lead to unnecessary computations or incorrect solutions. Always use the constraints to your advantage. Overcomplicating the solution is another frequent error. Many variations of this problem can be simplified significantly. For instance, instead of simulating reversals, you might just check if ARR and target are permutations of each other, or if they share certain properties. A great example is comparing the sorted versions of both arrays. This can often reveal whether target is achievable without the need for complex operations. Simplifying wherever possible not only saves time but also reduces the likelihood of bugs. A key insight for this problem is understanding that subarray reversals preserve the sequence of elements within the reversed segment, while the relative order of elements outside the reversed portion remains unchanged. This is crucial when designing an efficient approach. To handle this, you can use greedy strategies or auxiliary data structures like stacks to simulate reversals more effectively. Additionally, it's always a good idea to ask clarifying questions about the constraints. For example, confirming whether ARR and target are guaranteed to contain the same elements can significantly simplify your solution. Being aware of edge cases is equally important. Scenarios like empty arrays, identical arrays, or extremely large arrays, where n exceeds 10,000, can test the limits of your solution. Lastly, look for optimization opportunities. For instance, recognizing that reversing a subarray is equivalent to reversing a range in place can help you focus only on contiguous segments, making your solution more efficient. This problem is closely related to several others on LeetCode, which can provide additional context and practice. For example, problem 1460, make two arrays equal by reversing subarrays, focuses specifically on determining whether two arrays can be made equal. Another related problem is 581, shortest unsorted continuous subarray, where the goal is to find the smallest subarray that, when sorted, makes the entire array sorted. Problem 75, sort colors, involves sorting elements with a limited number of distinct values and often uses subarray manipulation as part of its solution. Finally, problem 31, next permutation, involves reversing a subarray to achieve the next lexicographical order of elements. Studying these problems can deepen your understanding of subarray operations and provide additional strategies for tackling variations of this problem. When solving this problem, there are alternative approaches to consider. One common method is the sorting-based approach. By sorting both ARR and target and then comparing them, you can quickly determine if target is achievable through subarray reversals. While this approach is simple and intuitive, it does not explicitly show the sequence of reversals needed. Another option is using a union find or disjoint set union (DSU) structure. This method groups indices that can be swapped via reversals and checks if ARR and target are consistent within these groups. Although more complex, this approach scales well for larger inputs. Finally, the greedy two-pointer approach can be used to identify mismatched segments and simulate reversals. While this method is efficient for constrained cases, it might not work for all variations of the problem. Each of these methods has its own trade-offs, so choose the one that best suits the specific constraints and requirements of the problem at hand. Great job! To recap, we tackled the problem by leveraging sorting to simplify the comparison. We highlighted how sorting and edge case analysis are vital tools in problem solving. Keep practicing, and we'll see you in the next session. Thanks for joining. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!